Every year, the world spends more than $20 billion on what seem like ordinary pieces of metal. Yet these are magnets, the hearts that drive every motor, turbine, and modern device. Behind their simple appearance lies a fusion of material science, metallurgical engineering, and atomic-level precision. From rare earth ores extracted deep underground, humanity must undergo dozens of complex stages involving purification, melting, powder pressing, sintering, and magnetizing. In today's video, join the factorin as we journey inside the factories where metals are transformed into force, and that force becomes the foundation of humanity's technological future. China currently holds an overwhelming dominance in the rare earth magnet industry, controlling more than 90% of the world's refining and manufacturing capacity. From neodymium mining operations in Inner Mongolia to sintering plants along its eastern coast, nearly the entire supply chain of magnet production remains under Chinese control. Starting in 2025, the Chinese government introduced a new export regulation requiring that any product containing even a fraction of rare earth materials sourced from China must obtain prior approval before export. The policy has forced many Western corporations to rely on Chinese authorization, raising concerns over a potential strategic leverage within the high-tech supply chain. With such near-total control over this foundational material sector, one question looms large. What would happen to electric vehicles, wind turbines, and even U.S. manufacturing itself if China suddenly stopped exporting magnets? The journey of a magnet begins deep beneath the surface of the Earth, in mineral mines where rare earth ores, such as iron, barium, or strontium, lie hidden among layers of rock. Geological engineers carefully survey each vein, rich in neodymium and other valuable elements, drilling multiple exploratory holes in order to pinpoint the exact extraction zones. When the ore is buried within hard rock, engineers employ precisely calculated blasting, determining both the amount of explosive and its placement so that the ore blocks remain intact, preventing fragmentation and preserving the quality of rare earth minerals. Unlike large-scale iron or steel mining, which often relies on massive destruction, this method requires meticulous accuracy and complete control. Once the blasting is complete, the extracted ore blocks are transported to collection yards using heavy-duty conveyor belts and specialized trucks. There, they are sorted into separate piles according to type, preparing them for subsequent refining stages. Throughout the extraction process, workers must take extra precautions, since rare earth ores sometimes contain uranium or thorium. Dust and toxic gases must therefore be minimized and strictly monitored to ensure safety. Each step in mining is closely supervised, laying the groundwork for transforming these seemingly inert minerals into powerful magnets that drive the world's modern engines and devices. After the ore blocks containing rare earth elements, iron, barium, or strontium are extracted and transported to the factory, they undergo preliminary cleaning to remove clay and surface impurities. In the milling section, the cleaned ore is fed into either a ball mill or a jet mill. For rare earth ores, the rotation speed of the grinding drum is kept steady between 20 and 30 revolutions per minute, while the compressed air pressure in the jet mill is maintained around 85 to 100 pounds per square inch. This process continues for 4 to 6 hours until the particles reach an average size ranging from 3 to 10 microns. Throughout the entire operation, the internal temperature of the grinding chamber is constantly monitored and must not exceed 180 degrees Fahrenheit in order to prevent any alteration of the crystal structure or loss of natural magnetic properties. Once grinding is complete, the powdered ore is cooled using inert gas, then passed through a multi-layer screening system that separates the particles according to their size. After the ore has been ground into a fine powder, the next stage is flotation, a process used to separate valuable rare earth particles from unwanted impurities. The powdered ore is mixed with water and special reagents to create a liquid emulsion. When air is pumped into this mixture, the valuable particles attach themselves to air bubbles and rise to the surface, while rock, sand, and heavier impurities sink to the bottom. Through this method, elements such as neodymium, samarium, and iron oxide are isolated, forming a purified powder ready for magnet production. Unlike the flotation of iron or common metal ores, this process with rare earths requires extremely high precision. Both the froth and the slurry must be carefully controlled, since rare earth ores have very low concentrations and are easily contaminated. The entire operation takes place inside a sealed tank equipped with dust collectors and chemical control systems to prevent the release of harmful dust or gases that may arise from traces of uranium or thorium within the ore. Each flotation batch typically lasts from 1 to 2 hours, allowing the valuable particles to adhere to the bubbles and float to the surface while preserving their elemental purity. After the rare earth, iron, or oxide ores have been floated and collected, the next step is to prepare the raw materials in the factory for alloy production. At this stage, engineers examine the purity, moisture content, and elemental ratios of each ore batch. For rare earth magnets, they mix neodymium, iron, and boron with precise proportions, while for ferrite magnets, the iron oxide powder is combined with barium or strontium. Every material is weighed and measured with exact accuracy to ensure that each finished magnet will have strong and stable magnetic force. Once mixed, the materials are transferred into sealed chambers or specialized containers to prevent contamination in any contact with air. After the raw materials have been mixed and inspected in the factory, the next step is melting and alloy formation. Before ignition, the induction furnace chamber is evacuated to create a vacuum and then filled with argon gas to completely eliminate oxygen and moisture, preventing oxidation that could destroy neodymium, an element extremely sensitive to air. Materials such as neodymium, iron, and boron are loaded into the induction furnace, where the temperature is raised to approximately 2,500 to 3,000 degrees Fahrenheit. The mixture is heated continuously for about 2 to 4 hours, allowing all metals to melt completely and blend into a uniform alloy. The heating duration is precisely calculated to achieve the ideal crystalline structure while preserving the integrity of the rare elements. For rare earth magnets, once the metals have fully melted, the molten alloy is rapidly cooled on a rotating drum within a few seconds. This technique of instantaneous cooling causes the liquid metal to solidify into thin metallic flakes with fine and uniform crystal structure. After the neodymium, iron, and boron alloy has been refined, it is ground into an ultrafine powder inside an inert gas environment to prevent oxidation. The resulting mixture appears dark gray with a subtle violet tint, and its particles measure only a few microns across. This magnetic powder is then placed into a high-pressure steel mold while being exposed to a powerful magnetic field reaching several Teslas. Within this field, millions of microscopic alloy particles begin to rotate and align in the same magnetic direction, much like countless compass needles all pointing toward a single pole. The entire process lasts only a few dozen seconds, yet it demands absolute control over pressure, magnetic intensity, and compression speed. Any inconsistency in the field or sudden change in pressure could disrupt the crystalline alignment, preventing the magnet from achieving its maximum pull strength. The outcome is a set of solid yet brittle alloy blocks whose crystal structure has been fully oriented. These are the magnetic blanks of the magnet, ready for the sintering and heat treatment stages that will unlock their final magnetic power. The freshly pressed alloy blocks may appear solid, but in reality they are as brittle as ceramics and possess no magnetic properties yet. To become true magnets, they are placed inside a sealed furnace completely isolated from outside air. Within the chamber, the temperature gradually rises to about 2,200 to 2,400 degrees Fahrenheit, hot enough for the surfaces of the powder particles to begin soft melting and bonding together under the weight of the metal itself. For the next 4 to 5 hours, the system maintains a stable temperature, allowing the alloy particles to compact tightly and eliminate even the tiniest voids between them. During this phase, the material transitions from a porous form to a fully dense solid, reaching nearly 100% of the density of bulk metal. And once the desired equilibrium is achieved, the temperature is slowly reduced over several hours, degree by degree, giving the crystal structure time to lock in the previously aligned magnetic orientation. Finally, an additional heat treatment at around 950 degrees Fahrenheit stabilizes the entire structure, completing the sintering process. After the sintered blocks have hardened and become solid, the next step is machining and protective coating. In this stage, the magnet blocks are cut, ground, and drilled using precision tools such as diamond blades or laser systems to achieve the exact shape and dimensions required by design. Next, the magnets receive a protective coating that guards against corrosion, moisture, and mechanical wear. For neodymium iron boron magnets, the coating typically consists of nickel, zinc, or epoxy, which not only shields the surface but also preserves the internal magnetic strength. Unlike ordinary metals, this protective layer is essential because neodymium iron boron is highly sensitive to oxidation. Without it, the magnetic force can degrade rapidly, compromising both performance and longevity. Once the magnets have been machined and coated, they remain completely inactive, showing no north or south poles yet. The magnetization stage is the process that awakens their true power. Each magnet is placed between the poles of a pulse magnetizer, where an extremely high electrical current, reaching between 2,000 and 3,000 volts, is discharged within just 1 to 5 milliseconds. This surge of electricity generates an instant magnetic field with an intensity of about 3 to 5 Teslas, which is tens of thousands of times stronger than the Earth's magnetic field. In that brief moment, all the magnetic domains inside the alloy align perfectly in the direction established during the molding process. This synchronization allows the magnet to achieve its maximum remanence, BR, and coercivity, HC. If the magnetic pulse is too strong, internal stress can distort the crystal structure. If too weak, some domains remain disordered, causing a noticeable drop in magnetic strength. After magnetization, each magnet's surface field is measured using a Hall sensor, and its polarity is verified through an automatic orientation tester. Those that fail to meet specifications are demagnetized and reprocessed, while the qualified ones are sealed and prepared for the final inspection and packaging stages. After the magnets have been magnetized, the next step is quality inspection and packaging before shipment. Each magnet is tested for magnetic strength, pole orientation, thermal resistance, and corrosion protection to ensure that every piece meets both technical standards and customer requirements. Specialized measuring instruments allow engineers to immediately detect any magnets with uneven magnetic force or incorrect pole alignment. Next, the magnets are packaged with great care, as their magnetic pull is extremely strong. Each piece is separated by non-magnetic shields or special plastic spacers to prevent them from sticking together or damaging their surfaces. The storage boxes are built to withstand impact during transportation, ensuring the products reach motor factories, wind turbine manufacturers, robotics plants, and electronic equipment producers in perfect condition. Packaging magnets also requires careful attention to magnetic fields so they do not interfere with nearby electronic devices, and so each magnet retains its full strength. Once the inspection and packaging are complete, the finished products are ready to power modern technologies, from electric vehicles and industrial robots to wind turbines, where every magnet becomes an invisible yet powerful heart driving entire systems. Once the magnets are fully completed, the invisible power within them begins to fuel countless modern devices and technologies. In the electric vehicle industry, neodymium iron boron magnets are installed in motor rotors, generating a strong magnetic field that enables smooth operation, improved energy efficiency, and maximum performance. In wind turbines, precisely oriented magnets are placed inside the rotor to convert wind energy into electricity efficiently, helping deliver clean power to millions of homes. Magnets also serve as the beating heart of industrial robots and medical equipment, where their powerful magnetic fields ensure precise motion, From robotic arms assembling cars to magnetic resonance imaging, MRI machines scanning the human body. Even in everyday electronic devices such as speakers, hard drives, and tiny sensors inside smartphones or computers, magnets play a vital role in generating magnetic fields, converting energy, and directing signals with remarkable accuracy. And so, we've reached the end of a remarkable journey, one that began deep beneath the Earth, where raw ore was unearthed, and ended with magnets that silently power the modern world. These small fragments of metal carry an invisible strength that turns the rotors of electric motors, drives the blades of wind turbines, and energizes the countless technologies that shape our lives. From extraction and grinding to molding, sintering, machining, magnetizing, and quality testing, every step in this process is guided by precision and human ingenuity, proof that even the smallest components can hold extraordinary power. If this journey inspired you, don't forget to like the video, share your thoughts in the comments, and subscribe to The Factorin to continue exploring the hidden stories behind technology and industry.